righty. With that, then there we go. Yes, I think we're good to go. So thank you for that way more fun part of the class than we're going to do right now. So we are going to be looking at vector subspaces again today. And just remember what the scenario here is. We know about a bunch of vector spaces. And in fact, we can add a couple more in here. We can add C infinity. We can add polynomials of degree n. So we are familiar with a bunch of vector spaces. What we explored a bit yesterday, and we're going to spend most of our time on today, is looking at possible subsets of these. So I know these are subspaces with the given operators that we work with. That was weird. Not just these sets, but these ones are also using the standard version of what we mean by plus and scalar multiplication in each of them. And notice it's a bit different for each of them. When I add a vector, it's not quite the same as when I add scalars. When I add functions, it's not the same thing as adding two scalars or two vectors together either. So just recognize that we are using different versions of plus and scalar multiplication, but the form of it works the same. And it's the one that you normally know and the one you're used to. So sorry, I lost my chat window here. I'll bring that back up. There we go. Perfect. All right. So the upshot of last class was, if we already know something's a vector space, and then someone says, well, what about this little piece of it? So you've got all of R. What if you take just the positive reals? Is that also a vector space with the same rules? So again, it has to be that same condition of the plus means the same plus and the scalar multiplication means the same scalar multiplication. If that's the case, you have two options. You can go through the entire 8 axioms for vector spaces, or because we're just looking at a subset, so we're keeping the same rules for the operations, we're just saying this little smaller piece of the set only, then we can take the shortcut and verify these 3 properties here, that the subset we have contains whatever the 0 element is for our bigger vector space. If we add 2 vectors in this subset, we stay within that subset. So we never have to branch out under addition. And also, if we scalar multiply any of the elements in the set, we also stay within the set. And we saw examples for and against that last time, like the line x plus y equals 1, or y equals 1 minus x. That had several problems, but one of them was it did not include the 0 value. So right away, we could say this was not a vector subspace. R2 is a lovely space. This is a lovely subset, but it doesn't quite fit the rules for a vector subspace. So the rules of vector subspaces or vector spaces would not apply here. Then we just moved that line down a little bit and we got something that did work. When we had our line go through the origin, or defined by all the points that satisfy x plus y equals 0, then yeah, R2 is a vector subspace. And then when we take this particular subset of it, we also get, technically the big thing is a vector space that satisfies all 8 axioms. And then we said, well, what about this little subspace? There we only had to check 3 of the conditions. Is the 0 vector in that set? If we take any 2 vectors in that set and add them, do we get another vector in the set? And we absolutely did. And if we scalar multiply, there we go here. If we scalar multiply any of those vectors, do we get another vector in the set again? And again, you can think of that as scaling and maybe inverting vectors. And of course, you stay on that same line if you do that. So we satisfied all 3 of those criteria. And that meant that this line is guaranteed to be a vector space or vector subspace with a lot less work than having to check all 8 axioms. We just have to check 3 because we're building off of our experience with a larger space, R2. Whew, all right, so that's all that. Where did we leave off in terms of examples? Right, we're now going to look at functions because honestly, this is where linear algebra kind of pays off in unexpected ways, in the sense that you've all been using vectors for ages now. Well, some of you for a year now, or 6 months, but they're fairly straightforward. Thinking about functions and different conditions on functions, that can be a little weirder. So let's see how this example here plays out. C infinity is a vector space. And I should put in the subtext here, with the usual function plus and scalar multiplication. We know how to add functions. We add them point by point. We know how to do scalar multiplication. We do that point by point as well. So C infinity is a vector space. We define a subset. This whole thing here is a subset of C infinity. And what defines it? Well, the condition we're putting on here is that our function at the point x equals 0 has to go through the point 3, y equals 3 or f equals 3. You know, that covers a lot of functions. I can make it pretty much any line. Okay, that's not a function. Let's try that again. There we go. That would work. We could have a parabola that opens downwards that does that. We could have some kind of cos 3 thing happening. So there's a lot of functions in there. There's an infinite number of functions, in fact, in that set. So U contains an infinite number of functions. All right, so it's big. Is it a vector subspace, though? Well, I'm hoping when you look at this list down here that you're thinking, no, just even looking at that first item, does the 0 element of my set, so 0 vector in C infinity is what we're talking about here. Well, it's not really a vector. If we're talking functions, we don't usually call it a vector, but this is our function f equals 0. Is that in the set? No. So 1 fails because the 0 vector in C infinity, or the constant 0 function is not in U. Why not? Because the constant 0 function has f of 0. Oops, bring that up here. If I look at the constant function, constant 0 function, it looks like this. And not surprisingly, it has 0 values everywhere. So it has 0 value at x equals 0, not f of 0 equals 3. And so right away, we can say that this collection of functions, this U value, this U set, does not satisfy the requirements for a subspace. I do want to just quickly mention that it also fails some of the other properties too. In fact, it fails all 3 properties. So I'm just going to highlight that quickly. It also fails 2, just for example. So I pick f and g both in U. And that means that f of 0 equals 3 and g of 0 equals 3. That up. Right. If I pick 2 functions out of the set, the thing that defines them being in the set is that they satisfy this going through the point 0.03. But f plus g at 0 is going to be f of 0 plus g of 0. So what happens when I add those 2 functions? I grab 2 functions from the set, and I want to know if the new function that I get by adding them together is also in the set. Well, if I evaluate that at 0, I'm going to get these 2 things added together. Of course, that's 3 plus 3. That's 6, which is not 3. So f plus g is not in this set U. Again, if to be in the set U, we have to be able to evaluate our function and get the value 3 at 0, at x equals 0. When we evaluate these functions, we get the value of 6 at x equals 0. This doesn't satisfy the criteria, so away we go. Exactly. Sorry, just checking out. Yes, Brian had the right answer there for the 0 value, the 0 element for C infinity. Now, just going back to this, okay, this is an example that's not a vector subspace, but could we tweak it? Like, well, hey, look, all these functions went through 0, 3. We have to have the 0 vector to start with. That's the first criteria. So obviously we knew that wasn't going to work. But could we adjust this a little bit? And of course, the answer is yes. We could try something similar. And we could say, we call that U, let's call this capital V. be a set of functions in C infinity such that, and just for fun, I'm going to change the X value up and show that that doesn't matter. What matters is this Y value. So what does this look like? Never hurts to draw a picture. X and F again. At 4, our graphs have to go through that point. And so I can imagine a function that goes like that, or a function that goes like this, or a function that goes straight up like that, or I could imagine the 0 function. The always 0 function would satisfy this criteria. And so we would say this V is a vector subspace. And we're going to go through the criteria for this. It's because, 1, it contains the 0 vector for C infinity, i.e. f of x equals 0, f of x equals 0. That's our 0 vector. Satisfies f of 4 equals 0. And I just picked this 4. You can pick any number you like. I just wanted to pick something that was not 0 itself to show it doesn't matter what x value you pick. The thing that seems to be dictating subspace or not subspace is this 0 value here. So does the 0 function, the function that's always 0, satisfy the condition that at 4, I get a 0 value back? Well, yeah, I get 0 everywhere, so that's done. Let's copy that over to the next page, just so we can refer to it. And also for 2, for any two functions, let's call them f and g, that are in my set V. So again, we're using functions from our set that we're interested in. F plus g is also in V, and we need to show this, so it's not obvious. What do we need to test? We need to test whether f plus g at 4 is equal to 0. So let's test f plus g at the point 4. And what do we mean by this notation here? It means, well, we're going to add the functions point by point. So really what we mean is evaluate the function f at 4 and then evaluate the function g at 4. But those are both equal to 0. A line here if you want explanations, because f, g both are in V. So this is more detail than we usually do, but just to make it crystal clear here, the whole point of these two functions being in V is that they have this condition they satisfy. And so that equals 0 as well. And so f plus g is in V too. And we made no restrictions on this at all. We just grabbed any two functions in this set, and we showed that when we added them together, we get something that also satisfies the same criteria. I'm turning purple again. Let's go back to that. All right. Last but not least, we are going to show basically the same structure as this, that if we pick an element from our set and we multiply it by any real number, we're also going to get an element in the set. Also, and I've written here, also 3 for any real, I'll use a real letter instead of alpha, I'll use A, and F part of our set V. Alpha times F is also in V. We're going to prove that. Our test is to look at what we get when we take our multiplier and multiply it by our function. And the way we test it at is at our criteria point here, which is 4. Well, it's going to equal alpha times f of 4. Now wait, what's f of 4 equal to? F of 4 equals 0 because f came from this set V. So we're going to get alpha times 0, and that's just 0 So alpha f is another element of V as well. So V is closed under addition, closed under scalar multiplication. There we go. All right. So let me just take a quick look in the chat there. We never decide what any of these things are. F is just a function. We used F earlier. I'm just going to go back a page to highlight where you saw the G's. The rule had an F in it. Didn't have to. I could have called this H and nothing else would change. H is none of that, H of 4. The key thing is I'm going to grab a function from C infinity, and the only thing it has to have or satisfy is that when I evaluate it at 4, I get a 0. The label here doesn't matter at all. It could be usually a letter, but any letter I liked in here, it's the same restriction. So when we say F and G here, it's just two functions that happen to satisfy that they're part of C infinity, they're continuous and infinitely differentiable. And when I evaluate them at 4, I get a 0 value. So there's nothing special about F in this thing. When I go from F to F and G, it's just tradition that will use F as this first part, because why complicate our lives? Let's use the first letter for functions. And then when we need a second function, we typically grab G as the next letter in the alphabet. It's not anything more than that. In terms of this is vector in R2, totally different thing. Like this question wouldn't make any sense because this set wouldn't make any sense for R2. That's a short answer. So for an R2 thing, we would have to define it as a valid subset for R2 going back to like here. So if I'm going to build a subset out of R2, I have to define it in terms that make sense for two-dimensional vectors. When we're talking here, we're talking functions, so it's a totally different starting set. And so the kinds of rules we use to define it will be different. Hope that helped. All right, so yeah, so V, this thing here that we just defined in the last page is a vector subspace. And so that's interesting. Again, just thinking of the pictures, this where all functions that go through this one point on the axis is a vector subspace. This set here, all the functions that go through 0, 3 is not a vector subspace. So somehow there's the zeroness in the output that has to be present to be a vector subspace. But even that, actually, we can tweak it a little bit further. Have something that looks very much like what we had before. So I'm going to take a set W, any function in C infinity where the value at 0 is equal to, I got to be careful, I got to be super careful here. It's that F of 3 is equal to F of 0. So these are two Y or output values. So this is X and F, and this is any function where it has the same value at X equals 0 and X equals 3. It doesn't have to be the same value every time, as long as it's the same value for a given function. It could be down here somewhere. So it could be, as long as those two values that we see here and here are the same as each other, then we satisfy this criteria. Grab a function, as long as those two values are equal, then away we go. So getting to Mark's question, the output doesn't have to be 0 here. There's nothing here about 0 values at all. But what we're going to find is that this is, W is, give it the name, a vector subspace of W. For the answer before, when we actually had a value, the key thing is, or the starting point is, the first thing we have to achieve. It's not enough, but it's a requirement. The function has to include, the function set has to include the 0 function. So if you have the 0 function, you know what it looks like. It's always 0 Y values for any X's. And so if your set only satisfies, it has to go through some point that's not 0, well, the 0 function is not in there. So what's interesting here is actually the zero function's fine, because the zero function happens to satisfy y at 0 and y at x equals 3, or everything's 0, so those two are definitely the same thing. I won't go through this one in the whole detail because it looks an awful lot like the last one, but you will see the same kind of trend. And again, this is just a nice way to sort of diversify our options. One is satisfied because the zero vector in C infinity, C infinity, is the f of x equals 0 for all x. And so f of 0 is equal to 0, and f of 3 equals 0 as well, which means that this zero vector is in W. These two things here are equal, and that's the criteria for being in the set. So the zero vector, the zero function, zero element. Again, zero element's a nicer way to phrase it here, because calling a function a vector makes people feel weird. Calling this an element, it's one element is one function. That I think makes more people feel comfortable with the notation and the terminology. For the 2 and 3, it's the same kind of logic as before. You can imagine what happens if I take an f and a g from the set. Take f and g from the set. As soon as I take those two things, I know that f of 0 is equal to f of 3, and g of 0 equals g of 3. And now we test f of f plus g. We want to know if I add these two things together. Let's make this a 2 here. Can't stop doing the whole thing. I wish I could stop. All right, test the whole thing. Well, what do we have here? We have f plus g of 0 is the same thing as f of 0 plus g of 0. That's what it means to evaluate a function at a point. If we have a sum, we just evaluate the sum of each of the functions. But then we have the property that f of 0 is the same as f of 3, and g of 0 is equal to g of 3. 0 is f of 3, because we're in the function, we're in this space, and g of 0 equals g of 3. But then what does that look like? That looks like f plus g evaluated at 3. That's from our definition of f plus g, what we mean by that. And so f plus g satisfies f plus g of 0 equals f plus g of 3. So f plus g is also in our set W2. So W is closed. I'll get right there under addition. All right, sorry, that's the end of that page. Go ahead. Maybe out loud I said the wrong thing. Everything on the page looks okay.
You wrote down the wrong thing on the page before.
Oh, the page before. Thank you.
You wrote
yeah.
Vector. Yeah. No, up top. W
Okay, sorry,
is
this
the
is
vector
actually true.
subspace of W.
Oh, gotcha. Thank you. Thank you. Yes. Yes. That would be kind of circular and not helpful. Thank you. Yes.
Actually, wait, would W always technically be a vector subspace of W?
Only no, because you don't know that it's a vector space in the first place. So
Right.
no,
Okay.
It'd be kind of circular logic again. So that's why we definitely want to start with something that we know is a vector subspace or vector space itself. Yeah.
But if we define W as a vector space, would it be a vector subspace of itself?
Yes. So if we said, is C infinity a vector subspace of C infinity? Yes.
Okay,
It's
got it.
a
Thanks.
subset of something that the key thing is it's something that you know already is a vector space. That's the only criteria.
Right. Okay, thank you.
Okay. So an example of number 2 being wrong, if you go back to that example we had with the straight lines. So way back here with this one here. Same criteria. Oh, I did it actually for the other one. I should jump forward. There's that one. Every example we've seen so far fails number 2, that if it fails anything. So here we said, let's grab 2 elements where the elements satisfy f of 0 equals 3. Well, that's not closed under addition, because if I take a function that goes through 3 and another function that goes through 3 here, when I add them together, I'm going to go through 6. Well, that's not part of the set, so that fails too. You can see more obscure ones. I'm not sure if they're in this week's tutorials or not. Anyway, you just bang through the list every single time. Sometimes it'll get through 1. It might even get through 2 and then fail 3. That's the way it goes. Just try them in that order, because that's usually the order that's the simplest to evaluate and assess whether something's going sideways for you. All righty. Quick time check. All right, yeah, we're good. Okay, so we can get even more interesting. We can get kind of calculus-y in this setting up of functions. For here, this is geometry. This is, I've got these 2 points, that's fine. It's not very interesting if you're taking calculus as engineers. This one is much more interesting because it has a derivative. I want all the functions whose derivative equals the original function itself. So f equals its own derivative. And for those paying attention, this is a differential equation. It's an equation that has some unknown function in it, and the equation involves the derivative of f, and we're trying to figure out stuff about f. Well, these are still functions. They're still part of the C infinity. That's why we can take derivatives safely. The 0 vector is in W here, because if f of x equals 0 for all x's, f prime of x, well, this function is constant, then f prime of x equals 0 for all x's. Okay, if we can imagine drawing the graph, here's our 0 function, our 0 vector, which is equal to our f of x equals 0 function. Its derivative is always 0 as well. It's just that flat line over and over and over again. Oh, okay, well, that means that f of x equals f prime of x for the zero element of C infinity, which means that the 0 vector satisfies our criteria, and so it's in this nifty little set W. Okay, so the 0 vector's in there. Let's go down the list. What's number 2? Number 2 is that if I add 2 functions in this set, I get another one. So let's pick f and g, both in W. That means that f prime of x equals f of x, and g prime of x equals g of x. We know that right away because that's what it means to be in the set W. And then what we're going to do is test what happens to f plus g. Well, to look at f plus g, we want to see if it satisfies this equation. So we're going to take the derivative this time. Last time we subbed in values. This time we're going to take the derivative because that's what defines our set up here. So let's take a look at the derivative and see if we can make it equal the original function. Well, we know how this works because derivatives are, wait for it, linear. I can expand this derivative into f and into the derivative of g. And the derivative of g Well, that's f prime of x plus g of x, g prime of x. But using these properties here, let's call this 1, let's call this 2. 1 and 2 tell us that we can replace this with just f of x plus g of x, which is the same thing as, I probably should have put more x's in here. I do apologize. Got a little sloppy there. That is the same as f plus g evaluated at x. Why did we do that? Why did we care? Because we said, let's take two elements from this set that satisfy the equal their own derivatives. And then we looked at their sum. We took the derivative of their sum, did a bunch of work, and we showed that, hey, the derivative of their sum is equal to the original sum as well. And that means that f plus g is also an element of W. And that means that W is closed under addition. All right. Now we still have to do the third one. I'm just going to check in. The zero vector is always defined. The zero vector is really defined once you know what your plus and your scalar multiplication are within your set. And so as long as you don't change what plus and scalar multiplication mean, and we're not allowed to do that for the subspace thing, then yes, it has to be the zero. The zero element for the big set has to be the zero element for the small set because it's the same addition and scalar multiplication rules. So just confirming that. Then just because we're on a roll, let's do this too. We're going to show that W is closed under scalar multiplication. So let's let A be a real and F be an element of W, which of course means that F prime of X equals F of X. Again, because it's in W, it satisfies that rule. And then we're going to test, sorry, I used A times F. We're going to take the derivative of A times F and evaluate at X. Well, what do we know about derivatives? We know a few things. I can bring the A out front, and we would call that A times the derivative of F of X. We're allowed to take scalar multiples out front and work with that. And so, oh, but wait, let's call this equation 1 again here. By equation 1, that is exactly the same as the original function. And that is the same as AF of X. So AF is an element of W2. And that means that W is closed under scalar multiplication. 1, 2, and 3 are all satisfied. Satisfied. So W is a vector subspace of C infinity. In other words, it's some kind of coherent set of all possible functions. This set of functions who equal their own derivatives, somehow it has this structure where I can add elements in that set and still stay in the set. I can scale them and still stay in the set, and the zero elements in there as well. So I'm just going to pause there while people are copying. I was writing quickly there. And then I'm going to look at what this means in terms of the pictures. So in terms of graphs, what do these graphs look like? Well, we know what one of the graphs looks like. We know the zero function is in there. So there's that. There's, f of x equals 0. There's the other canonical example. If I have a function that equals its own derivative, well, that'll be something like, an awful lot like, e to the x. F of x equals e to the x. What else fits that description, though? Well, it turns out that any multiple of e to the x, because we actually said this, right? Any multiple of a function in the set is also in the set. So I should be able to get 2 e to the x. And so that we can do that. So 2 e to the x, f of x. equals 2 e to the x. And let's change color here a bit. We could also have a half. F of x equals a half e to the x. We can also flip it upside down. We can multiply by negative values. So we could have negative e to the x. Negative e to the x. Anything in that collection, and they all share this property of this expansion going that way. Notice e to the negative x would not work. Why not? Because if I take the derivative of e to the negative x, I actually get negative e to the negative x, which looks like this. So it has to be just e to the x with some multiplier out front. Can't have a shift on it either. It's basically, this is it. This is the family that satisfies it. We'd have to do some work to show that, but this gives you a good intuition for why that might work. And again, what we're looking for here, what we're getting out of this little process is we now know that if I can find one of these functions, so it's a vector space. So this collection of all these functions makes up a vector space. That means right away that I know I can freely scale them. I can take any example I want and I can multiply it by any real number, and that's still a valid solution. I can just play with those things any way I like. I can include negative values. I can add two of these things together and I know it's still a solution. So all of that machinery comes along for free just by saying this W forms a vector subspace of all the possible continuous and infinitely differentiable functions. Even though our motivation is probably coming from something like population growth, because that's the kind of thing that shows up in a population growth scenario. So I'm going to touch on this next little follow-up here. I will go back to the slides afterwards, not a problem there, but I won't be right now just because, again, it's so hard to get through the notes on time. I apologize. This is where pre-recorded are nice because there's a little bit more flex, but this should hopefully ring some bells. What functions, when we differentiate them twice, give us the negative of the original? What functions, when you differentiate them twice, give you the negative of the original? Well, there's two answers to this. There's the mathematical answers, which is sine of t and cos of t. And there's also the answer that it's all the things, all the motions that satisfy a spring system. Spring, mass, with a spring constant of 1 and a mass of 1 kilogram. So if you want to describe the motion back and forth of a mass attached to a 1 Newton per meter spring and 1 kilogram mass, it's going to be sines and cosines. And I'm not going to go through the details here, but we can confirm that 1 is satisfied because the zero function, when you differentiate it twice, is still the zero function, matches itself. And not too surprisingly, if you add a sine and a cosine together, if you add solutions to this, you can satisfy that equation as well, because again, it's derivatives. It's exactly the same structure as the last example, where you can swap the derivative and the sum because they're both linear. You can exchange the order. And likewise for scalar multiplication, you can take a scalar multiple out front. And so this is where we get the strong result that we can add any sine and cosine together, or any multiple of them, and it'll still be a solution. It'll still be one possible motion of this spring mass system. So again, that's something that's very powerful to be able to say in one line, just linear algebra card. Doomph. All the solutions to this are whatever solutions we find to this, we can add them, subtract them, scale them by real numbers, and they're still solutions. We can't break that system. Any one of those values is perfectly valid. So that's kind of where we're going with linear algebra, is to be able to pull it out when we get to more complicated cases with functions. That's one of the ways we're going. And yes, it's exactly like 171. That's we're borrowing heavily from that. All right. So that's one set of proof types, and you've seen both examples where it's not true, and examples where it is true that a subset is a vector subspace, or it's not. It satisfies the 3 criteria, or it misses one or more of them. The other kinds of proofs that we're going to show here are more like the set proofs back from week 1-ish. And they're also handy because they just let us say, how does it work when we have more filters on a set? For example, if we have a big set here, imagine C infinity. And what if we put some set V in that set? And they said, oh, there's some other criteria, W. And so this could be that the two values at 0 and 3 are the same. This could be that its derivative equals itself. What can we say about the intersection? Do we have to go through all the work of, not too much work, but still, do we have to go through the work to show all three axioms are true, even for something like an intersection? And the answer, fortunately, is no, because we can use set stuff to prove that if we have two sets that are a subset of, let's call this now, what do I want to call this? Let's call it V, with both A and B, both A and B being vector subspaces of capital V, a vector space. Okay, so again, this is the big picture. Here's V. I've got something I've already proven is a vector subspace A, and I've got another subspace B. They all satisfy all three axioms. Those guys are all good. I want to study, not with an X, I want to study this intersection here. I want to study A intersect B. Okay. And by study it, I want to know, can it also be brought into the fold? If these are vector subspaces, A and B, can I show that A intersection B is also a vector subspace? Yes, the answer is yes. And we are going to prove it. And the only way to prove it, of course, is using the three axioms. Keep in mind, though, we're not saying the power of math is generality. We're not saying this is R, Rn, R2, function spaces, doesn't matter. Anytime I have two sets that define vector subspaces, the intersection of them is also going to be a vector subspace, no matter what domain we're talking about. So let's dive into this. And of course, it's going to be the same three stages. We're going to prove all three properties. We need one, the zero vector, zero element from V must be in A intersection B. That's what we want to show. Proof. All right. The zero vector is in A. Why? Because A is a vector. I'm just going to use VS for vector space or vector subspace. It actually has all the same criteria or same properties. Vector space. If A is a vector space, one of the properties that has a zero vector in it. Also, you can see where this is going. The zero vector is in B because B is a vector space. And so 0 has to be in A intersect B because 0 is in A and 0 element is also in B. And that's what it means to be an intersection, is that you're all the things that are in both A and B. Phew, that was easy. Yeah, so this is the zero value. We've got that for free. The other ones feel almost as silly in some ways. If we're going to look at 2, we need F and G being in A intersection B. So I'm going to grab any, let's call it U and V. Sorry, we were using functions earlier. Let's change it to more abstract vectory kind of things. We need to show that if these two things are in A and B, then U plus V is also in A intersect B. All right, so how do we work with that? Well, we know that U and V are in A because they're in the intersection. And that means that U plus V is also in A. Why? Because A is a vector subspace, closed under addition specifically. Right. If I have two elements of A, and I've already proven all the rules apply to A, then U plus V has to be an A as well. That's what we spent our whole time proving before. See where this is going, I hope. Hey, guess what? U and V are also in B because they're both in the intersection. So they have to be in A and B. And of course, B is also a vector subspace or vector space because B is a vector space. Vector space 2. And so U plus V has to be in A intersection of B because U plus V is in A and U plus V is in B. We just said those two statements here. If we're in both of those sets, then we're in the intersection. And that means that A intersection B is closed under addition. I can add any two elements and get another element in that set. Pause there for people to catch up, and then we'll take a look at the last part of it, which is, of course, exactly going to be the same kind of logic, that if we get an intersection, we're going to be closed under scalar multiplication. So 3, if, sorry, we need a real, so we need A element of the reals, and U is an element of A intersection B, then A times U is also in A intersection B. And a proof for that. So U is an element of A. That means that A times U is also in A. Why? Because A is a vector subspace, is a vector space. And one of the things every vector space guarantees you is that it's closed under scalar multiplication. And V is an element of B, tells us that A times V, sorry, U again. U is in B, A times U is also in B, because B is a vector subspace. And that means that A times U is also in A intersect B. So the condition is that A and we didn't prove it, we assumed it. So we said, if I'm coming along, I'm walking through my math homework, and someone said, oh, here are these two sets. They happen to be vector subspaces. Let's call them A and B. So they are known vector subspaces. Then we're saying, hey, what if this is my peanut butter and chocolate. What if I put them together? What if I do the intersection between them? Can I take a shortcut? Can I already say that that is or isn't a vector subspace if I already know that A and B are? So we're relying on that given. If you don't have that information, you can't use any of what we're doing here for sure. But sometimes you have that nice property that someone told you, or you already figured out that these two sets are vector subspaces already. And now what we just showed is that if we intersect those two that we know are vector subspaces, the intersection is also a vector subspace. So 1, 2, and 3 implies satisfied, implies, so I'll put it here officially, if A and B are known, oh, I can't write, are known vector spaces or vector subspaces technically, then A intersect B will also be, it'll always also, but this sounds awkward, will also be a vector subspace. Yeah. Yeah, so these proofs all seem incredibly circular. Yeah, not gonna lie, that is a property of the feel of them, but they aren't circular. What we're doing is we're starting off always at one element of the thing we're considering, and then we're showing that that combination, sorry, one element of what we're starting with, so U here, and we're showing that some related element is also in the set. So it's not going in a loop. We're saying, let's take one element of the set and show that when I multiply by any scalar, I'm also in the set. So it can feel that way, but it's actually not. So the challenge as you practice this is to get familiar with that, I think. Okay, I'm gonna take you 2 minutes just because this one's an easy one. We just did intersections. What if we had those same two sets, A and B, and what if we union them? Would that be okay? And the answer is, so no guarantees. No guarantees here. There's an easy counterexample, which is if I have in R2, one line here, let's call this my A, which is the set of all X's and Y's in R2, such that Y equals 0. That's a perfectly valid vector space. And let's get this other one over here. Let's call this B, which is the set of all X's and Y's in R2, such that all the X's are equal to 0. It's not that hard to show that, let's imagine this point here. Let's take this point, say 3, 0, and the point 0, 2. This is an A, this is in B, but the point 3, 2, which is what we get when we add those 2 points, is not in A union B. So we get bad things happening, or we can get bad things happening in this kind of example where if I take two elements of the union, those guys are both in the union, but if I add them together, I get something that's even further outside, that's outside the union. And so this would not be a vector subspace. All right, I think that was the last slide I wanted to cover today. Yes, perfect. We are going to talk about linear combinations, which somebody mentioned in the chat there, but that's the core content for today. So I'll stop the recording here and also open the floor for questions.